To random variables.
Okay. Hi, everybody. So welcome back to another lecture in this computational thinking course in spring 2021 semester. And today we're going to start talking in more detail about probability, randomness, which you can also call stochastic behavior. So stochastic is just another word for random, basically. And so we'll be talking about what you could call random variables. And I don't know how to get rid of this live docs thing that's right there. So let's start off by looking at a few of the Julia, just summarizing a few of the pieces of Julia that we're going to see today. There are a couple of functions like sum and which takes the sum of a collection of, so in all of these, in all of this description, capital S is some collection of data which lives, for example, in an array. There are various types of container object that it could live in. So sum of S will take the sum, literally the sum of all of the values contained in this collection, in this, for example, array. Rand of S will do some kind of draw something randomly from that collection. Mean and standard deviation will calculate those statistical quantities. And so some of these functions that we'll look at come from different packages. And so we're trying to be more explicit about which packages you need to load to get each function. So for example, so when you load Julia, there's a library called base automatically loaded. So you don't need to do anything special and all of these things will be available. But if you need the mean function, for example, at the moment, you need to load the statistics package. And it turns out that that is actually a standard library package in Julia, which means that it comes preloaded with any Julia installation. So all you need to do to load it is do using statistics with a capital S, the name of the package. So we put using and then the name of the package to load the package. And that will bring into scope all of the names that are exported from that package, and mean and STD for standard deviation are two of those function names. And then there are various other packages that we're going to use. And so this first cell up here is actually loading in, specifying some versions of packages that we need, and loading in all of the packages that will be used during the notebook. That's what, if you've been wondering what this strange syntax is. And so we're working on a better mechanism for doing this package specification. So we're going to use a function called countMap, and that lives in statspace.jl. So this is separate from the statistics package, and this is actually a separate package that does not come pre-installed. So you will need to do, package add statspace, so which we did in the cell I just showed, and then using statspace to load it in.
But anyone using this particular Pluto notebook doesn't have to do anything.
Exactly, yeah. But this Pluto notebook also automatically loads all of these packages for you. So we've already used the plots.jl package a few times. Today we'll look at histograms and bar charts, which have these functions defined in that package. The colors.jl package we've used as well, and we'll be looking at using the distinguishable colors function, and then that's probably all we'll have time for. So let's start off by talking about randomness. So how can we get random numbers or random objects in Julia? So by the way, what does random actually mean? That's a very difficult philosophical discussion. And actually, we can't really generate true randomness in a computer. But there's something that's almost as good, which is sort of something that just looks very random. We won't enter into the details right now about how that works, but maybe we can.
My codes have random bugs all the time. What do you mean I can't get randomness on my computer?
So actually, one of the ways of getting randomness on a computer is actually just to track all of the processes that happen from the time you turn the computer on, and when exactly all of the key presses happen, and that will effectively generate some randomness for you, because the next time you turn your computer on, you won't have exactly the same sequence of key presses at exactly the same moments. So you can actually use that as a source of kind of true randomness on a computer. So Julia has sort of abstracted that all away, and it just gives us this function called rand. And rand is actually a very versatile function. So what does it do? So if I give it a collection, so here's a collection, 1:6, we know that's a range. So that contains, in some sense, all the numbers between the integers between 1 and 6. So when I do rand of 1:6, it will pick one of these at random. So one of the objects in this collection, it will pick at random and return it. This is a strange function from a mathematical point of view because I'm giving it the same input, but it gives me a different output every time. So actually what's happening is there's some other implicit hidden function, which is sort of some random number generator object, and that is actually being modified. And so that's hidden from us. So it looks like it's just generating random numbers. So I'm just going to run this a few times, and you can see that sometimes it spits out the same number twice in a row. And anyway, it's giving me random numbers between 1 and 6. And yeah. And so, of course, I can give just some other vector of random numbers, like these few prime numbers here. And I'll do rand of that vector. And it just picks one of these numbers at random, one of these 5 numbers. And so, you can ask, well, how often should I expect it to give me the number 2? And we'll discuss that in a bit. What other kinds of containers or collections can I use? You can actually use a string. So here's just a normal Julia string, the string MIT. And when I do rand of that string, it just treats the string as a collection of characters. And so it just gives me a random character from the string. And so note that a string in Julia has these double quotes, a character has single quotes, and it's a special different object called char, which we've already seen. So we've already used this function, quite a few times, especially in the homework on languages. But now we're seeing it in more detail. So you can also do this this cute thing where you can take the character A colon the character Z. So that gives me a range. So what is this object here? It's actually a kind of range, right? So the type of this is a so-called step range with char inside, so characters inside. And then, so that's, the collection of all the characters from A to Z. And when I take a random element from there, it just picks one, equally likely and returns it. Now, what about if I don't put anything inside here? There's actually a default value. So there's a default here, which is actually float 64. And so it's going to take it's going to give us a random number between 0 and 1, a random real number, or rather a random floating point number with 64 bits of precision. So you'll be working a bit with floating point numbers on homework 5, and we'll talk about it more later in the course.
What happens if I type rand without parentheses?
Oh yeah, great question. So what happens if we type rand without parentheses? Well, we're referring to a function called rand, and when I execute that cell, indeed, it tells me that, oh, that thing that I just asked for is just the function called rand. And it tells me, oh, look, it has 119 methods. So I'm not sure, have we talked about methods before? So what is a method? It's just a version of the rand function. So, this rand that takes in a sequence of characters is actually a different version of the function or a different method than the rand that takes in, some other object like a string. And so there are actually all these different versions or methods of the rand function. We can see them all with methods of rand. And it just gives me a list of all the different ways that I can call rand. And you can go and see exactly, you can click on one of these and go and see exactly how it's defined in the source code, which we won't do right now. Okay, so yeah, so rand is that's why I say it's very versatile. These are all the different things that you can generate randomness from, basically. So for example, here we took distinguishable colors of 3. So what does that do? It's from this colors.jl package. We've already used it a couple of times. It's just a function which returns a vector of this many colors and using some particular algorithm to make them distinguishable. Maximally distinguishable for a human being, sort of visual mechanism in our eyes. So if I do distinguishable colors of 10, it just literally returns me a vector of colors. Right? So if I do type of this thing, it'll tell me that it's a vector of color objects. Oh, I guess I should just make a new cell for that. And so now we can choose, so since it's a vector, we can just do the same as we did before and just choose a random one of those. Even though these are color objects, it'll choose one of these colors at random, right? So that might be something. So I'm just reevaluating the cell, running the cell with Shift Enter several times, and I see again, it sometimes reproduces the same, sometimes gives me the same color, and often gives me a different one of these 3 random colors. Okay. So far we've only generated one random object from a collection. How about if I want, to generate 10 random objects from the same collection? I can do that easily. So I could do that just by making my own comprehension, array comprehension like this. So random 1:6 will throw a six-sided die, and then I'm going to repeat it 10 times with the usual array comprehension syntax that we've been using a lot. And that will produce an array of 10 items. And when I rerun it, because rand is generating new randomness, every time I'll get a new random vector of 10 items. But actually, the people who wrote Julia realized that this is a very common thing to want to do. And so you can just actually add another argument to rand like this. So rand of S, this collection, capital S, and then n, this number of elements, will actually do that for me. So I don't have to write this comprehension myself. And actually, it's even more general than that. You can make arrays of random numbers. So here's a random matrix of 1 through 6. So again, I give 1 through 6, and then I give the dimensions of the array. For example, 10, 12 will make a random 10 by 12 matrix of these die rolls. And when I run that again and again, I get a different random matrix each time. And of course, I can do the same with colors. And so here's a nice colored matrix. And you can see that sometimes you get these sort of connected regions of colors, and sometimes you don't. So you could start to ask questions like, how likely is it that I get a region with sort of, 6 connected cells of the same color, for example? So you can start to ask questions like we've been doing in the previous few lectures about how, what is the histogram, what is the distribution, how likely is it that how many clusters of size 1 do I have? How many clusters of size 2? Where by cluster, I mean these connected colors. And that's actually very a super important question, for example, in statistical physics and percolation problems. So for example, is it possible to get one cluster of a single color that crosses the whole system from one side to another? That's the key question in percolation theory. And you can investigate those questions numerically. If I make, so for example, could I make yellow be more probable than the other colors? And then how likely does it need to be in order to have a cluster that crosses the whole system?
This is totally relevant to virus transmission.
Yes. Very good point. Yeah. So if these are people in a city and we're representing the space, space in a city, then and you have connections to your neighbors because you go and have coffee with them, or you talk to them over the fence, and you might end up sort of unfortunately projecting some droplets from your mouth towards them. Then you can represent that as a connection on this space. And as Charles says, that that can model, can a virus actually cross the city? And so we'll be going into that subject in much more detail later in the course, in the context of networks. So this is basically some kind of network, and you want to know how connected is the network. Okay, and just for fun, we can also use random images, right? So here's an image of a US penny. For some reason, the quality of the picture is less good than it was. Okay, so a US penny has heads and tails, just like any other coin. And so we just downloaded an image and split it into the head piece, so that image actually contains both the head and the tail. And so using our image tools that we've looked at in the first couple of lectures, we can just split that into 2 pieces and call them head and tail. And then I can make an array of this head image and the tail image. And I'm just going to sample from that and make a 5 by 5 matrix of those images. And this all sort of just works in Julia. It's pretty neat, and that can give us a nice intuition for sort of randomness.
Can you execute that line a couple of times?
Yeah.
Just for fun?
Yeah, exactly. So I
don't know. I just enjoy the movie, the emerges.
Yeah, that's a good idea. Yeah. So we're sort of, it's as if we're shuffling around. Actually, it looks like visually like we're shuffling around. Which ones are pennies and which ones are heads. But actually, what we're doing is sort of randomly flipping each one independently, and whether this particular one comes out heads or tails next time is independent, does not depend on what the other values are in this simple way of sampling.
Could we add a coin toss sound effect to Pluto? Is that not now? Not now. But I'd like to hear it. Like
good idea, yeah. But you could, of course, say, oh well, I actually want to do some process where I flip this coin depending on what its neighbors are, and that is again a very important kind of process in many different contexts. For example, in statistical physics. Okay. So what we've been doing is what's called uniform sampling. So what do we mean by uniform? We mean that each possible object that we're choosing from has the same probability as the other ones. And what do we mean by sampling? We just mean picking a random object. But that picking might actually be, we might actually want to pick different objects more often, certain objects more often than others. And we'll see how to do that in a minute. So what do we want to do? So we've got our collection of objects, and we're generating a lot of, say, let's think about rolling a die. We have 6 possible values, 6 possible outcomes, and we want to know if we roll the die 100 times, how many outcomes are 1, how many are 2, etc. So let's start off with just a coin. So we can flip a coin with heads and tails, with the string heads and tails, and we'll take 10 tosses. And sorry, I can't put a space there. I can put a space there. And what we're actually doing is we want to count how many times we get heads and how many times we get tails. So here's the result of tosses. It's just a sequence of a vector of Julia vector of strings containing strings. So it has the string head, then tail, etc. And we want to count just how many times does head occur and how many times does tail occur. So you can probably think of various ways to do that counting. And we'll do that in a minute as well. But let's just see that we can actually load in a package that does it for us and gives us a kind of nice answer, which is this count map function. So, it's called that because it's counting and somehow mapping that count over the data. And so I've called the vector of outputs, of outcomes, tosses, and the result of this counting is toss counts. And we can see what type is that outcome. It's actually a new type called dict for dictionary. So if you're familiar with Python, for example, you probably use dictionaries a lot because it's very important in Python. But in Julia, it's not used so much as in Python, but it's definitely used in many circumstances. So you can see that what is a dictionary? Well, it takes some label called a key and a value that we have assigned to that label. And we write that with this arrow, which in Julia you would actually write as equals, an equal sign, and then a greater than sign. And so you can actually make an object which is tail arrow 3, and that particular object is called, the type of that object is actually called a pair. And so a dictionary contains a sort of, you can think of it as containing a sequence of pairs. And we can ask for what is the value of tail that corresponds to the key tail inside this dictionary by indexing as if it were an array, but the sort of index is now this string itself. So that's called a key in computer science. Okay, so count map is just designed to return a dictionary which gives us the numbers of value, or the number of times that each of these occurs.
Can you once again just run that a couple of times and watch the effect?
Yeah, so I'm just going to run that several times. I'm generating new data. You can see the data up here, and then we're counting it down here. And because we're using Pluto, everything just updates when I rerun this. So you can see that, okay, so you might expect to have roughly the same number of heads and tails, and often we do have roughly the same number, but sometimes it gets more extreme. And, again, you can ask the question, how often will you see, for example, 8-2? So we haven't actually seen 8-2. Oh, there we saw 8-2. How often are we now going to see 9-1? There was a 9-1. How often will we see 10-0, which is possible, but very unlikely. So that's the kind of question that we want to ask. Okay. And so we can actually calculate that probability, right? This is just the number of times. So if we have the number of times that the outcome was tails is 4, then we can call the probability 4 divided by 10. And so that we can calculate that like this. And as I was generating the data over and over again, so let's go up to now 100, for example, and so there were 45 tails on this run, and the probability is therefore 0.45. And so, of course, we all know that, intuitively, that we expect that as we run more and more simulations, so if we go up to sort of 10,000, we expect the probability of getting tails to somehow become closer and closer to 1/2. And that seems to be what's happening. And so again, we want to ask the question, well, how far away from 1/2 might it be? Okay, so far we've only been doing uniform sampling, where all of the options, the possible outcomes, have the same probability, or they're chosen, in an equal, even way. How could we do the opposite? How could we actually make it so that I chose one possible value more often than another one? So we could literally think of a physical coin where we tape, some extra piece of lead or something on one side of the coin. So when I flip it, it's more likely to land on one side than another. So that's literally what we mean by a weighted or biased coin. And if you're an unscrupulous casino, you might do that. And actually, I mean, in roulette, for example, you would expect all of the values, all of the positions of the roulette wheel that it could land on to be equally likely, but the casino guarantees that it makes money on average by adding a 0 and even a double 0, where nobody makes money except the casino. And so they're effectively making the game weighted in their favor. So we shouldn't, play roulette basically, because we're guaranteed to lose on average. So how can we model that? So what we want to do is say something like, okay, the probability that I'll get heads, I want it to be 0.7, and the probability that I get tails, I want to be 1 minus that. So probabilities always have to sum to 1 because of the way we define them as just dividing the number of outcomes by the total number of outcomes. So when we sum up all of the possible outcomes and divide them by the total number, we should get 1. And so, so a simple way to do that would be to say, oh, well, if I toss 10 coins, what I want is for, on average, 7. So basically, I assign the outcome, the word head to 7 of those outcomes, to 7 of those possible values that I'm going to generate out of 10, and tails to the other 3. So one of the ways to do that in Julia would be like this. So I'm defining a function called a simple weighted coin, and I'm generating a random number, random integer between 1 and 10. So that's going to, as I said, generate those with uniform probability, so equally likely. But then I'm saying if the outcome is between 1 and 7, if it's less than or equal to 7, then I'm going to return the string heads. Otherwise, I'm going to return the string tails. So just a couple of points about Julia here. So we have if, else, end, which I'm not sure we've actually seen before. That's how you do an sort of if, then, else in Julia. So if this, then do this. Else, otherwise, do this. And you could have an else if something as well. With so I'll write that. Could have else if. That's actually one single word, else if. That's another option. And then otherwise we'll return tails. And so you see that this if statement is actually going to return a value, return either this or has a value. The statement has a value, heads or tails. So basically all statements in Julia have a value, and you can use that value. So I could actually even say sort of outcome equals, and then put the if statement here, and then outcome would sort of collect that value from inside the if statement, and then I could return outcome like that. But I haven't done that. I've just, well, let me leave that in, and then I'll make a new cell without those. So the question is this simple weighted coin 2? Okay. So these are 2 different versions. I can't have 2 different definitions of the same function in Pluto in 2 different cells. So that does actually return a value. So what's going on? The if statement returns a value, and then the function itself returns the last value that was calculated inside that function. So you don't even need this return statement, actually. You could just put outcome, and it will return that value. But I find it better, more readable to actually explicitly tell it what I want to return. And by the way, one exception to this, everything has a value, is a for loop. The value of a for loop is actually nothing. Right, so if I do for I in 1 to 10, sort of whatever, nothing, and then I say result equals that, what is the value of result is actually empty. But that's actually, there's a special value in Julia called nothing, and the value of result is actually that nothing, but that nothing is displayed as literally empty. Okay.
Are you getting something from nothing?
No, I'm getting nothing from something. Okay, so yeah, so that was an example where, okay, it was easy to do because we had this sort of 7/10. I could have written this as a fraction, actually, 7/10 and 3/10. And so it's clear that, oh, in that case, I just generate, random integers between 1 and whatever the denominator of my fraction is. And then it's clear that hopefully that should be the correct thing to do. But what if I have just an arbitrary real number p between 0 and 1? How could I generalize this? And so what we actually want to do is generate, some uniform values that can be anything between 0 and 1. And the way we do that is with this rand with nothing inside, that, as we saw, gives me uniform random numbers, real random numbers or floating points, random numbers between 0 and 1. And then I just want to check when is that output actually below 0.7? And that should occur fraction 0.7, a proportion 0.7 of the time. In other words, with probability 0.7. And so if I do run this cell again and again, I should get some trues and some falses, and the proportion of trues should be about 0.7. And the point is I can make this like 0.314159, and then I should get trues and falses that proportion of the time. So of course we want to check if that's actually true. But before we do that, this is called a Bernoulli trial with probability p. After the Bernoulli family in the 17th century basically were some of the creators of probability theory. And so Bernoulli of p is a function that I'm going to define where I pass in the value of p I want. And this is a much shorter version of the code that we just had, right? So what am I doing here? I'm saying generate a uniform random floating point number between 0 and 1, check if it is less than p. And as I showed up here and forgot to mention just now, a comparison like less than in Julia also returns a value. So I don't have to check, is this equal to true? It just sort of is true, right? And so what I'm doing here is this is returning true or false. And I'm assigning that as the output of this function. And so if I actually run this function once with some input value like 0.7, it does return true or false. When I run it a few times, it mostly returns true, but sometimes it returns false. So that is a nice short way to write that function, and you should sort of process what's going on here step by step to make sure you know. So this, again, we've seen this before, I guess, but this is defining a function with this short form syntax where equals defines this function name with this input argument to be the output with output whatever's on the right hand side of the equal sign. So here is where we're actually computing, using count mount to count up how many times we get false and how many times we get true when we flip its biased or weighted coin with probability p, or we do a Bernoulli trial with probability p 1,000 times. And I can, just in Pluto make a nice slider. So with 0.7, I get approximately 700 out of 1,000 being true. And let's just run that a few times. And so we can see that this number is always hovering somewhere near 700. And the other number is hovering around 300. If I move that down to 0.23, or let's say 0.1, you can see that about 1/10 of the time, indeed, I get true coming out, which is what I wanted. So we have successfully generated a non-uniform thing. So what is that thing that we're generating? It's actually what we call a random variable, which is what was the title of the lecture. So what is a random variable? It's a bit of a bad name, in my opinion. So, random is okay because there's something random going on. Variable is a bit strange because, it's not really a variable in the sense of computer science. It just means an object, a thing, such that it can actually take on different values every time we sort of run an experiment. There's some experiment somewhere and we're running it, and there's some output, and that output is this the value of that output is one of the possible values of this object called a random variable. And then what we are interested in is the probability that that random variable object takes each possible outcome. And that set of correspondences between the possible outcomes and the probability of those outcomes is what we'll call the distribution, the probability distribution of that random variable. So how can we, so that all sounds very abstract. So how can we actually make it more concrete? Well, we can visualize it, of course. That's always what we want to do. We've just been playing with all these numbers that they don't make much sense. We actually want to see something. So how can we do that? We'll use both bar charts and histograms for that. So we want to count, we've been counting how many, sorry, comment? So we've been counting how many times things have occurred. So let's actually try and visualize that, as I just said. So let's roll a die to start with. So a normal fair die. So we'll generate uniform random outcomes between 1 and 6, integers between 1 and 6, 100 times. And so, by the way, excuse me, if we don't know about the function count map, how can we actually count up, do these counts by hand? Well, we could literally just, write some little piece of Julia code. So here's an example of one of those pieces of Julia code. So there's another function count that we forgot to add to the list of functions that we're using. What does count do? It actually takes in a vector of Boolean values, trues and falses. So let's look at that. So what are we doing here? So this dot equals equals. So when you want to check if two things are equal in Julia, you do equals equals, so double equal sign. And then the dot, I guess we've mentioned a few times, does something called broadcasting. So we're doing element-wise comparison. So we're comparing each element of this output vector roles with 1. And when we do that, we get a vector of trues and falses. So is the first one equal to 1? No. Is the second one equal to 1? No, etc. So we get falses until this 1 here, and then we get a true. And now we're just going to count how many of those are actually true. That's what this count function does. So you could also use sum, actually. When I do sum, I get the same answer, but it's just sort of conceptually nicer to do count. It counts how many of them are equal to 1. And so that's what we've done here. We've done that for each I in 1 to 6 and put that in an array comprehension. And so we get out all of the counts. But if you think about it from a point of view of computer science, if you have a very big vector of data, maybe 100 million, maybe it doesn't fit on your disk. Maybe actually 100 million is pretty small these days. Maybe 100, 1,000 million, 100 billion bits of data. That's pretty normal size for, for example, click data from big websites. You could have 100 million clicks a week or a day even, maybe. Sorry, billion, I mean. And so you want to go through and see, well, how many people clicked on this element of the website? How many people clicked on that element? So you literally want to do this count. But what we're doing is very inefficient, actually, because we're looping through the whole data set and just picking out the ones and then storing that number. And then we're looping through again and storing just the 2s, and then again and storing just the 3s. And so, the computer scientists on the call will think, that's a terrible idea, and we should just be looping through the algorithm a single time, the data a single time, and at each time we see a value, we should store that in the appropriate place. And so, of course, that would be a better algorithm, and that's what count map actually does. So you should think about how could you actually implement that yourself? And we'll probably put that on the homework. So now we want to plot these numbers, right? So I have 6 numbers, which are the numbers of times that 1, 2, 3, etc. appear in my data, in my dice roll data. Now I want to plot that. And so we'll do that in a bar chart. So I'm sure everybody has seen bar charts before. So there's 2 different concepts that we're going to use, a bar chart and a histogram, and they are actually different. So a bar chart is for data which is categorical. So it has categories, discrete values, discrete categories. So in this case, the discrete categories are just the numbers 1, 2, 3, 4, 5, and 6. And so you can see that the bars are separated, and the width of the bar really does not mean anything in a bar chart. But the height of the bar tells me how many of that category I saw. So in this case, I saw 21s and well, some number of, it's actually going off the top. So why is it going off the top? Oh, because of this. Yeah. So so there we go. That's the complete distribution. And so this is telling us, just the height of these bars is telling us how common each one is. And then we added this horizontal line, which tells us what we actually expect the result to be, right? We expect, I was claiming that these generate uniform random variables, random numbers, random variates, sorry. And so they should each be the same height, and that height should be the total number of die rolls divided by 6. And we're seeing that actually, well, we're pretty far away from that. And so now I'm just going to pull down that slider. I don't have a slider, sorry. Going to pull down this data generation cell so that we can just change that number and rerun. So I'm just going to first rerun the cell a few times, and we see that this histogram updates. And actually, when we have a very few die rolls, we can be pretty far away from this sort of average value. But if I just fix my intention on this 6 column and I rerun it a few times, you can see that sometimes it's below the average, sometimes it's above the average. So you can imagine that if I reran the whole experiment about 1,000 times, and I sort of averaged over these histograms, you would find an average histogram that was around bar chart, sorry, that was around this middle value. So again, that's something you can do for homework.
You add some more zeros?
And now I can add another 0, exactly. So if I add 1 more 0, oh, it seems to be closer to that mean value. So the scale changed, by the way, right? So I'm just going to regenerate things with 1,000, and it doesn't get so far away. When we zoomed out, it looks sort of the same, but it doesn't get so far away. And when I add another couple of zeros, it's actually really pretty close to this average, but it's still not exactly equal to the average, right? It's sort of almost never going to be exactly equal to the average. So, that's what we're seeing there is basically what's called the law of large numbers, that as you increase this value, you should get closer and closer to the mean or expected value that we think should occur. Even though, in principle, even in 100,000 rolls, you could get 0 6s coming out. You could be all the way down here. It's just extremely unlikely that would happen. And we'll never actually see it when we run a simulation, because we can't do enough iterations. Okay, so that's nice. So that was a bar chart for categorical data, so for data which lives in discrete categories. Now we're going to change to think about actual numbers. So here we were just thinking of the labels of a face of a die as labels. We're just thinking of labeling the faces of a die. So we could have called these, cow, sheep, pig, goat, or whatever on the different sides of the die. And we're just saying which one came out. Now we're actually going to move to thinking about those as actual numerical values. So we're going to roll multiple dice, and then we're going to think of the outputs as numbers that we're going to sum. So let's write a function called roll dice with an argument n, where we're going to sum up n dice rolls. So rolling n random dice between 1 and 6, that gives me a vector, and then we're going to sum over that vector. So we're actually doing arithmetic, and so we're really thinking about actual numbers, and yeah. And then we're just going to write a function called experiment, which is roll dice of n, and now n is a variable that I'm going to change with this slider. So I'm also going to have a number of trials. So we'll start with a small number of trials, 100 again, 10 to the power 2. And so here is the output of my data when I run the experiment a certain number of times, trials, and I make another array comprehension. So let's actually look at what that data looks like. So that data looks like this. It's basically, currently it's the same, basically the same plot because I'm using n equals 1. But now I'm using a different function, which is this histogram function. And so a histogram is like a bar chart, but now the width of the bars actually matters. So what we're measuring with a histogram is areas. The area is now supposed to be proportional to the value of yeah. So what we're actually doing with a histogram is saying there is this that the area of this bar is, let's say, equal to or proportional to the total number of data points that fall into the bin or region defined by the bottom of the bar. That's what's happening. So what happens when I take this n and move it around? Oops. So let's go to 2 dice. So I'm rolling 2 dice and I'm summing up the results. So the minimum possible value I can get is 1 plus 1, which is 2, and the maximum possible is 6 plus 6, which is 12. So here's a 12, somewhere in here there's a 2, and there's 100 of those numbers, and I'm just going to see how likely each of them is. And you probably know that the answer is that the most likely is always 7, because there are basically 6 possible ways you can get 7, and there's only 1 possible way you could get 2 out. And so we should have bars which are height 1 and 7, right? So here I have approximately 2 outcomes, and here I have approximately 20 something outcomes. So in this particular case, I actually have more 7s than I was expecting, or fewer 2s maybe than I was expecting. And so of course what we need is more data. So let's just up the number of trials to 10 to the 4 maybe. And then we see that now I have something like 250 2s, and I have something like 1,500 7s. And so there's a ratio of about 6. Okay. And so we actually end up with this sort of triangular shape for the probability distribution of the sum of 2 dice. So I'm just going to keep on adding more dice. So this is the sum of 3 dice, then the sum of 4 dice. And you probably maybe know what to expect as I add more and more dice together. What we're seeing is that the shape of the resulting curve seems to be, something that is, after I reach a certain number of dice, basically stops changing too much. And it looks sort of bell-shaped. And let's actually add even more trials. Oops. That was dangerous. And as I add more trials, it really gets nice and symmetrical and nice and sort of almost smooth. I could probably add more bins now, 200, and we start seeing a pretty nice bell-shaped curve. So here's, by the way, a picture of a bell, and indeed it looks pretty similar to this curve. And so, yeah, and so again, what is this histogram doing? It's counting the number of data points that fall within the width that's defined by this bin bottom. Okay, so let's do that again. So as we change the number of dice, the picture, the graph seems to be sort of settling down to a particular shape, but everything else is changing. The y-axis is changing and the x-axis is changing. So somehow it seems like, well, there's something interesting going on. It seems to be converging to a shape, but I'm not respecting that because my axes are changing. So what I need to do is actually find the way to scale the axes or scale the data so that I get something which sort of really stops changing. And if I can do that, then I've actually sort of discovered a mathematical truth or mathematical idea in this data, which is that there's some limiting distribution going on, and it's something, and this distribution is actually converging in a sense to, how like a function, and the shape of the function is converging to another function. So what is that function? Is the famous normal distribution or Gaussian distribution, and which has an actual analytical formula. So how can we do this scaling? So that's what we're going to do now. So the first thing to do is that we can look at the y-axis, and we see that the y-axis is just growing and growing because it's the sum of more and more dice. So that, when I sum up 10 dice or sum up 20 dice, obviously 20 dice is going to give me a sum that's something like twice as big as summing up 10 dice. So the first thing to do is, well, then I should just divide by the number of dice, basically. So that's effectively what we're going to do. And so there's, but what we're actually going to do is divide by the, divide such that the total area of all of these bars is 1. But that is basically what I just said. So effectively, we have to divide by the number of dice, but then we have to worry about the width of these bars as well. And so there's an option to this histogram function, which is norm equals true. And that will actually normalize the output so that the total area of the bars is 1. So there are various other options for this histogram function, and I sort of summarized them a bit further down in the notebook. Let's just comment what they are. So I pass in the data I want to take the histogram of. Then alpha is the transparency. So you can see that the grid lines are showing through slightly. I hope you can see that behind the data. So that's useful just to sort of see exactly how high we are. This legend equals false. If I put legend equals true, it puts this key thing back on with the labels of the data, and that's sometimes useful to have, but often it isn't so useful, so we'll just turn it off. And then bins is the number of regions that I'm splitting this x-axis up into. And I can actually specify either a number of bins that I would like or the actual sort of edges of the bins themselves. So yeah, they're often called bins. I think that's the standard term for this. And then I can specify a color for the bars with a C or color keyword. And there are actually a zillion different possible colors you could use. So here we did light salmon 1. So there's a link to further down in the notebook to the colors.jl documentation where you see all of those color names.
Whenever I look at that link, I feel like I'm in a paint store, like you've got more options. Mm-hmm. You never know how.
Yeah, maybe I should just go to that link. But
yeah.
Where did I put that? Oh, maybe it's further up. Oh, did I get rid of it? Oops.
Oh, no.
It's too easy. It's still too easy to accidentally delete cells, unfortunately. And oh, there we go. Yeah,
there it is. You got it.
Here is a list of named colors. Right. So let me just put a little title here. Options for the histogram. Options for plotting functions. There's really options for general plotting functions, and there are a couple that are specific to histogram. So I was trying to separate out which ones are specific and which ones are general. Yeah. So. And I go to this link, and you see, as Alan said, here's, like these paint swatches or whatever they're called. There's all these different colors, and they all have these names. And so you can just call them by name, but also you can just give the RGB values, which are these triples that we've already seen of red, green, and blue numbers. You can also specify like that. Okay, so sorry, I now lost my window. That's the problem when I do that. Where is it? It just disappeared. Oh.
Did you
I closed.
Go back from the paint. Just go back there.
Right, I just have to. Right. Sorry. Yeah. Okay. Great. So
we don't see it yet.
You don't see it. Yeah. Sorry.
Yeah. Now we see it.
So yeah, so just to finish off, so we're going to normalize the y-axis by that trick. So when we do that, and we, change. Let me drag this n slider down again, and we add more and more dice. So here's the number of dice. You can see that the y-axis basically has stopped changing. I mean, it's changing a bit, but basically the scale is now pretty much fixed. So I could actually fix the scale, maybe 0 to 0.05. And so when I do that, you can see that as I add more and more dice, okay, it is changing a bit, but gradually it sort of settles down.
Well, there's the x-axis thing.
Oh no, it's not settling down. Yeah, it's not settling down. Yeah, so the problem is it's spreading out more and more because on the x-axis. So actually, I was saying the wrong thing.
Why don't you just do both the y and the x-axis, and then people will see.
But now, so now the problem is, what I was saying before was that the values were getting bigger and bigger. That's on the x-axis, sorry. Yeah. So now we need to normalize the x-axis as well. So how are we going to do that? Well, we see that this distribution now has some kind of width, and we already know about width of distributions from last lecture on PCA. And so we know that what we need is the standard deviation, or any other measure of the width actually will also be fine. So for example, the mean absolute value that I did last time. But if we take the standard deviation, we can do that with this std function that I mentioned from the statistics package, standard library. I'm going to call sigma that standard deviation. So here are the mean and standard deviation of this data. So the mean is 168, that's roughly here. That seems like the mean, the average value of this distribution, and the standard deviation says that it's 11, and that's about this sort of width of sort of half width of this distribution. That's good. And so what we're going to do is demean the data and then divide it by the standard deviation. And that's something, again, you're going to do in homework. And so when we do that, and I'm going to drag the n down yet again, you can see that now, basically, the distribution is pretty much fixed in place, and it is actually converging to some limit, some limiting shape that gets sort of smoother and smoother and more and more bell-like, basically. And so as I take n higher and higher, that is actually something happening where it's literally converging to some sort of limiting distribution. And that is the normal distribution or Gaussian distribution. And what we're plotting is called the probability density or probability density function of that distribution. And here it is in red. It's given by this explicit analytical expression, exponential of minus x squared over 2, all divided by this normalization constant, square root of 2 pi to make the area 1. And you may well have seen that before. And you see that it really does fit extremely well to this sum of dice. So as we take more and more dice and we normalize, we scale everything in the correct way, we see that we actually do really get closer and closer to this limiting Gaussian distribution.
I love the way that red curve just hugs the histogram just so beautifully. It's just a pleasure to look at.
Yeah. So actually, that's really why the normal distribution is so ubiquitous, so common in nature, is because actually if you take almost any sequence of independent random variables with certain technical conditions and you add them up, the result will have this kind of distribution. And that is the content of the famous central limit theorem. So it's a theorem about the limit of, what we just did was take a limit as, or what we're trying to do is take a limit as the number of dice goes to infinity. And when we scale everything in the correct way, and this turns out to be the correct way, everything converges to this sort of this distribution, at least close to near enough to 0. Everything converges to this distribution. What happens far away from 0 is different.
You mean this is not only special for 6-sided dice?
That's right. If we went back and now did 3-sided dice instead of 6-sided dice, we would get the same thing happen. We could actually do that, right? So that we just do three-sided dice, and the same thing happens, right? So
that.
That's pretty nice.
I
Yeah.
bet it doesn't work on 12-sided dice.
So the only problem might be if we ever summing up too many things and we get an overflow, but I don't think that's going to happen. So.
Not with 12 dice.
Yeah, so here, like this distribution is sort of much wider and flatter than it used to be because we're summing up bigger numbers. But when we scale everything in the correct way, suddenly it pops back into this normal shape. So yeah, so it's very, this is something that of course you see in a probability class. But personally, I saw this in a probability class and I had no idea what was going on. But if you actually see it numerically, in a computational thinking kind of way, it's suddenly pretty intuitive as to what's actually happening to some extent. So that's the end of the hour. So I think that's a nice place to stop.
Let me again remind everybody that there's Monday's a holiday at MIT. I guess it's what replaces what we used to call spring break, but we don't have one this semester. So the next class will be Wednesday, a week from today.
Yeah, so exactly. No class on Monday, March 22nd. And the next class will be Wednesday, the 24th of March, 1 week from today. Okay, thanks everybody.
Everybody in internet land out there and the students.